Yes. Okay, dot product. Let me back up one more time. Dot product is not multiplication. Don't say u times v. Okay? That will give you the wrong impression. It's u dot v. The product, or the dot product is, it's where you multiply the x's together, you multiply the y's together, and you add them up. Write this down. The solution to a dot product is a single number. It is not a vector. Almost every other operation done with vectors will actually end up giving you a new vector. The dot product is not one of those things. Your answer will be a single individual number. So in this case, you had 4, 5, and you had 2, 3. If I use the dot product, what's the solution?
23.
If you multiply them together, you get 4 times 2 plus 5 times 3, which gives you exactly 23. There is something very important to note about the dot product. The result of a dot product tells us something very specific about the vectors you are looking at. Okay? The result we look for is 0. If the dot product, write this down, if the dot product is 0, then your vectors that you started with are perpendicular. They're 90 degrees apart. If or they're called orthogonal. If the dot product equals 0, then your vectors are perpendicular, or what we will call orthogonal. Your book and lots of the material will say the word orthogonal. You can just simply translate that as perpendicular in your mind.
Orthogonal?
What is orthogonal? Like, where does that come from?
Can you draw it?
Ortho is a term of perpendicular.
I thought that was mouth.
Well, in mathematics, it may very well mean mouth. Okay. In vector fields, when you're looking at three-dimensional pieces, when you have the orthogonal objects, it's three-dimensionally perpendicular. Now,
I think it's bones. It's bones.
true. Example 2. Let's try this one. See what you get for that. U is 2, negative 1. Shh, listen. V is 1, 2. Find the dot product. Real quick.
You said 3, 1, and what?
2, negative 1. It's on the board. And 1, 2. Orthodontists try to make your teeth straight.
But teeth are bones.
Orthopedic surgeons don't just do teeth, they do
Bones. Yeah, they do bones.
V equals what?
Shh. Here we go.
You're wrong. Face it. You're wrong.
There's something I want you to look at on the screen. Shh. Look up on the screen. If you were to draw the vectors, look at example 1. 4, 5, and 2, 3. If we were to draw a real rough sketch of those vectors, you can clearly see that the angle between those is very small. In fact, they're closer to parallel to each other than they are to perpendicular. Hence, when we got 23 as a result, now that doesn't tell me anything about the angle. It simply tells me that these two vectors, as you can clearly see, are not perpendicular.
Yes.
But if you look at the second ones, you can see u dot v equals 0. And so you get 2 times 1 and then negative 1 times 2, which would give you 0, showing you that those two vectors are, in fact, perpendicular to each other.
So every vector we're going to deal with is in its origin?
If I'm just telling you the vector itself, remember, vectors never tell you position, so we're just naturally going to put them at the origin to compare them. Otherwise, if I told you, I would tell you the points, and then you would subtract the points to get the actual vectors.
Is there a number that we come up with that tells us whether it's parallel or not?
That's a great question. Listen. He says, back up. When would we know if the vectors are parallel to each other?
That was weird. Don't do that.
If the vectors are parallel to each other,
They have the same slope.
they would have the same slope. So how do you find slope? Y over x. So if you have the vectors, isn't the component form of the vector that's changed in the y over the change in the x? Or It's the changes in the y and the x. That's what vectors are. How do you find a vector from a point? Terminal minus initial. You subtract the x, you subtract the y. So if you divide the vectors, y divided by x, that's going to end in the same. That would tell you they're parallel to each other. Now, they might not be the same length. I don't care about length. I care about slope. There's other ways to do that too, and we'll get to those later, but let's look at the next example. Let's talk about finding, well, back up to that one example where you had two vectors, right? How would you find the actual angle between those two vectors if it's not perpendicular? This is the formula that we're going to look at now. Absolutely. Everything I do today you will need to know. Okay? Cosine of theta equals the dot product of u and v divided by the magnitude of u times the magnitude of v. Write that down.
But you're giving us these formulas.
These formulas I will give you all tomorrow. Anything we do today, I don't have a problem giving you the formulas. This finds the angle between any two vectors in space. Not this. Okay? When we found the tangent inverse of y over x, that's finding the true angle at the origin. This is telling you, well, if I had two vectors drawn like we did previously, what's the angle between the two vectors, not the vector and the x-axis? So, let's do an example. If we had 4, 3, and 3, 5, using that formula, what are the three parts I'm going to have to find prior to actually using the formula? I need to find what? I need to find the dot product. What else?
I don't understand what the
The magnitude of each of the vectors.
Why?
You tell me. What's that formula tell you?
Oh, that's the lines mean magnitude?
The lines mean magnitude.
Oh, I thought that was.
The absolute value?
Yeah.
That's exactly what it is. But the absolute value of a vector is how long is that vector? What is the distance from start to
You
finish?
have to do the magnitude of both and then multiply.
So find the magnitude of each one and work this out. Okay, so the solution would be this piece. You find your dot product, which should have been 27. That was the easy part. The second thing, I find the magnitude. That's the square root of 25, or just 5 for you. V turns out to be a little more complicated. You're going to have the square root of 34. And literally, I'm going to type it into my calculator just like this. 27 divided by 5 times the square root of 34. But be careful. Be careful. Shh, listen to me. If you type in 27 divided by 5 and you hit times the square root of 34, it won't work. If that whole part is in the denominator, you're going to have to put parentheses around the whole bottom part when you type it in. If you don't, then it's going to think that the square root of 34 is on the top. And that's going to give you something crazy off.
Is that 22.2?
Yes. So 22.2 is the answer. I think it actually turns out to be like 22.17 or 22.18, but round to the nearest tenth of a degree. Be careful in this. Shh. This is easy, but if you don't know how to type it into the calculator, no matter how smart you are, your calculator is going to spit out the wrong answer and you won't realize it. Okay? Now, I want you to try, let's go back. Shh, listen carefully. Let's go back to the actual original number. Shh, listen. I want you to find I'm going to put them individually in a minute, but the first, see the 2 here in example 1? I want to find the actual angle between example 4, 5 and 2, 3. So that'll be here. Right. Well, no. This is between two vectors. This is different. Shh. Find the angle between those two vectors. Now remember, we said these two vectors are really close to each other. So you should expect that your angle will be pretty small.
How do you find angle again?
Well, you just did it.
Oh, okay.
You just did it.
I didn't realize it was the same equation.
Now don't confuse, that's not this angle. I don't want the vector's angle. I want the angle between two vectors. That's the key phrase you look for. Angle between two vectors. If it's just the natural angle, then I'll say, what is the...
I'm going to take my pencil.
Whoa,
Oh, thanks.
sorry. If it says the angle of a vector or the direction of a vector, that's the first one we looked at. Okay, here's the final solution. Make sure, let's look at the parts. Okay? In order to work this out, we had to find the dot product. Okay? We had to find the magnitude of each vector. When you're using this on your calculator, listen to me. It's better to use the symbolic square root than it is to round it. So literally leave it as the square root of 41 and square root of 13 in your calculations like you see on the screen. Okay? Then we plugged it into the formula and worked it out.
Where does that come from?
It's from your magnitude.
Square root of, I'll go back in, watch.
But it's 3 squared plus 5 squared, I thought.
3 and 5. No. Shh. Look at V. Shh. They're calling that one V, and they're making this one U. And so if we do V, that's going to be equal to the square root of 4 plus 9 to give you the square root of 13. I'm not really sure. Doesn't matter, because I just want to know the angle between the two of them. You could have called it U and V or V and U. The person that actually worked this out did it backwards like that, but that's not a problem. If it's just for the angle between the two of them, it won't make any difference. Okay? For us, we're not going to... I mean, there is an issue of, are you talking about the larger angle or the smaller angle? Because technically, if I were to... if I drew the angle like this and like that, there's two ways to know angles, but we're always going to look at the acute angle in between. Okay? Unless I tell you something specifically, go counterclockwise to find the angle, but you should know the differences. Okay? I'll state those. And the diagram, if it's something like that, I'll actually state the diagram and draw that in for you. Okay. One more thing. Work.
No.
Okay. Look up on the screen, or look up at me. Shh. I can hold on to this cart. Look up right here.
And you're doing.
Okay, watch. If I'm going to pull this cart along, okay, on the ground, my arm is not pulling directly in front of this, right? So as I change the angle that I'm pulling at, that I'm changing the force required to pull it, right? So what we talk about is work. The angle that I pull at affects it. The amount of force that I'm using to pull this cart across the floor and how far I have to pull it is all an exertion of energy. It's all about how much work was done to get the cart to move across the floor at a specific amount of force and a specific distance that I had to pull it. Okay? Now you have two formulas, and please, if you go to read this in your book, I suggest that you don't. It actually gets quite confusing. It's going to talk about a projection of U onto V and talk about the horizontal components, and it's going to get kind of really very linear algebra type. So don't do that. What you want to look at is a couple of formulas. Let's look at an example. We're going to use this particular formula. This formula is nice because it works it out in easy pieces for you to understand. Number one, look up here at when I'm holding on to the cart, my arm is what I'm using to pull, right? So that, if you look at the angle from the horizontal to up my arm, it makes a certain degree. Shh, listen. I'm going to be pulling with a certain amount of force, that's F, and I'm going to travel across the floor so far, okay? That distance is the magnitude of vector PQ, right? So you had this, let's say you're pulling this object, okay, and you're going to make it travel from here to here. So This is vector. You're going to go from P to Q. So if we wanted to know the distance, we would find the magnitude of vector PQ. That would be your distance. Your theta is going to be located right there.
That's all it gives.
And then the magnitude of the force would be the force pulling on that object. So here's what we're going to tell you. Here's what I'm going to give you. The angle that I'm pulling at, let me erase that. The magnitude I'm going to be pulling at is going to be 30 degrees. We're going to be using a force of 45 pounds. And I'm going to be dragging that 20 feet. Can you tell me how much work is done when I pull that across the floor?
Yeah.
This is the last piece of today's lesson. Force times the cosine of the angle, which is really the x component, and the angle that I'm looking at. So what was the answer?
779.43.
Let me erase my drawing before I get all messy with it. It's 779.42. The unit is kind of weird. Not that this is a big deal. Is foot pounds. It's a measure of distance per pound, right? Anyway, this is called work. So make sure that you know when I ask you for work done over an object, you're looking for the angle. You're looking for the force applied, and you're looking for how far did I travel across the distance. Now, let me give you a little bit of instruction here. Shh. I could make this a lot more complicated. Listen to me, not your neighbor. Shh. If I tell you, I may tell you that it traveled from one coordinate to the next coordinate. I may give you the position. In other words, I might tell you the points that represent the vector. I'm going to give you the actual force vector, but you have to find the magnitude of that vector. You might not be given the distance it travels, but you might be given the coordinates that it went from one place to the next. You'll have to find that distance. It usually is a horizontal distance, so finding that is just a matter of counting. Okay? I might not give you the actual angle between the vectors. I might actually give you the two vectors and ask you to find the angle itself. But if I've asked you for work, you should think I need three things. I need the angle between them, the direction you headed, and the force applied. I need the actual amount of force or the magnitude of the force vector. And I need the actual distance or the magnitude of the direction vector. How far did you travel? If you have those three things, you can plug it right into that formula in the red box, and it gives you the work done. That's the easiest way to think about work. Your homework comes from page 519. It's 1 to 24, or sorry, 3 to 24, multiples of 3, and then a couple of the work problems, 33, 36, 47, and 51 and 52. Tomorrow we will go over these, answer any questions you have, and then we'll have a short quiz, probably the last half of class or so many minutes of class, after you've had a chance to ask questions.